Started. Let's go ahead and get started with this next topic. So I did switch the order of them, and I think that's going to work out okay. We actually covered the next topic, which was how to do shaders and understanding vertex shaders in terms of more of architectural details and syntactical details, and you got some experience with that in the lab as well, so that kind of overlapped nicely. What was originally intended to be prior topic to that is viewing and transformations. And so it's a little backwards in that the primary purpose of vertex shading is to do these viewing and transformation related things. So we're learning kind of the theory about why we do that and how we do that after we learn the mechanics of how we write the shader. But ultimately, the vertex shader to do a typical 3D viewing transformation is just one line of code. So we don't need a really advanced shader for that part. So we understand shaders at least to some extent. Now let's understand, mathematically what we're doing with those viewing transformations, as well as what does that mean in practice in real-world OpenGL. Let's go back to our big picture, which has not changed. Our fixed function with some programmable parts, a graphics rendering pipeline that starts with our 3D models and ultimately converts them to a 2D array of pixels corresponding to the display. This topic is all about that geometry or that vertex stage. Not just the mechanics of what a shader is doing that we already covered, but given that we specify a vertex or a triangle, given these XYZ positional attributes, what does that ultimately correspond to where it's going to be drawn in our window? It's kind of a fundamental task associated with writing an application in OpenGL or any other graphics API. We'll start with 2D transformations, which is just kind of easier to draw and easier to visualize what's happening. Every single thing we talk about in the 2D space where we just have X, Y coordinates has a direct analog in the XYZ three-dimensional space. So we don't really lose a lot. This will be 2x2 matrices, and then it'll have a 3x3 matrix equivalent of what we are doing. And the math is all entirely the same here. It's easier to put it on a slide. It's easier to talk about 2D transformations first before we start diving into 3D. By and large, we have gotten by without this for our application so far because we have done effectively all of that geometry processing at the application stage. We have done, in some sense, if you've done anything that had kind of a 3D look to it, even for some of our 2D kind of movement and transformations up until this past week, we have done that geometry stage by specifying our attributes such that it looks more 3D, or it looks like things are in different locations relative to each other, or it looks like potentially things are moving. That is still valid in some sense. The math of what we can do at the application level on the computer, on the host side, can be exactly the same as the math that we can then tell our vertex shader to do. It's just going to be incredibly more efficient to do so on the device side, on the GPU side. Because we can specify what that transformation needs to be for a given scene once. And then as we're processing all of our vertices as they come through, those inputs don't necessarily need to change. Another way to think about that is our shapeshifter application, which while we were doing scalars with that, you will see we could have wrapped it into a matrix as well. We'll see that today. We are specifying the same exact triangle every single time. So we really only have to copy that data over once. We only have to commit that buffer once to our device memory. Then as we fetch that buffer, as we actually process those vertices, it's that transformation that then changes. So this advantage of doing it on the geometry side and hardware is really more about performance than anything else. We'll talk about the math behind it, what it means to actually do it either way. So the kind of general transformations we typically want to be able to do in our geometry stage is to do things that you would have maybe learned about, in junior high perhaps. Where we may want to translate an object. We want to be able to move an object. That's what we mean by translation. We want to potentially rotate an object. Again, when we say object, just think of a triangle, that's fine, or think of something composed of triangles. We want to move that triangle, we want to rotate that triangle. We may want to make our triangle larger or smaller, that's called scaling. There are some others as well. We may want to reflect the triangle across an axis or across a line. We may want to modify x in terms of y or y in terms of x, that's called shearing our objects. In general, a 2D transformation would just be an algebraic function in both x and y dimensions. So we'd have an f sub x and an f sub y that take in the initial values x and y and produce a modified, a changed value x prime and y prime. In a vectorized form, it is shown as down there. In general, the transformations we can apply given a function f sub x and f sub y are arbitrary. We can do all sorts of things given an input x and an input y, and mathematically they're all perfectly valid. We do not necessarily need to have what is also referred to as kind of affine transformation, where lines correspond to lines and lines of parallelism correspond to lines of parallelism. If we were to do that and have so-called nonlinear transformation, it wouldn't be as straightforward as just transforming the vertices themselves. The nice thing about these affine or linear transformations we are going to do is we can actually just transform the endpoints or the vertices of our triangle, because our lines are going to be preserved. And kind of the term linear means here, it's lines still become lines. We only need to transform those individual vertices, and the end result is as if the entire primitive itself has been transformed in that way. If we were to do a nonlinear transformation, it's going to be harder to deal with. If we're not preserving lines, if we take input vertices, it's not clear what the end result should be. This is total arbitrary nonlinear math here, assuming our transformation function was something like this. Given an x and y value, calculate x squared over 4 minus y plus x plus 1, or the y function we have down there. And if our input was a set of primitives corresponding to a nice little house where we have triangles and quads here representing a house, what would the end result look like? Can we do that math in our head? No, and I didn't even try to do the math. It would look something bad, right? Something kind of arbitrarily nonlinear and bad. You wouldn't be able to do so by just transforming the individual vertices. You'd actually have to transform every fragment inside that. In general, we don't need to do that to get the type of 3D manipulation we want to do for rendering a scene. So fortunately, while we will use linear transformations, it's not really a compromise. It is giving us the kind of effects we are generally interested in seeing here. Our translations, our rotations, our scaling, our reflections, and our shears here. So if we restrict ourselves to these, well, what we're going to find is that it's very computationally efficient. We can represent it all in a single matrix representation. It keeps our linear properties of our incoming geometry such that we only actually need to apply the transformation to the vertices. That's why we can do it in the vertex shader. We don't have to do anything else. It's also general for matrices. You can compute the inverse of it. So if you want the inverse and kind of revert the transformation, one can do so. The only issue, if you want to think of it as right now as an issue, is that while we can have this general linear transformation of ax plus by plus c, we can represent the a and the b part as a simple matrix vector multiplication. The c part becomes then a vector addition. So at least in this formulation of our linear transformations, there's really two steps associated with it. There's a matrix vector multiplication and then a separate vector addition. You can think of the matrix vector part as what's handling the rotation, handling the scaling, and then that plus t, that vector addition, as being the shifting of those points around. Think of your vertex shifter example or shape shifter example from MP3. We were doing that via scalar values, right? There was a scale x, a scale y, and a shift x and shift y. It was called something like that, right? Where we could scale the x values and y values and then translate the x values and y values. And those values can be directly thought of as a sub x, b sub y, as well as c sub x, c sub y for that translation. So while we didn't implement that one via a matrix operation, we could have. The advantage of not doing it as a matrix operation is that the uniforms are a little bit simpler. It's scalar math, so it's testing a few other things. But if you really want to test whether your matrix stuff is working, both in terms of the uniforms you're passing, as well as the other resulting loads and stores that are necessary for that, one way you could test your MP3 stuff is not to worry about the cube, which could expose some other challenges, but just take the shapeshifter and convert it to a matrix equivalent operation and confirm it matches what you are otherwise going to be getting here. I think I can go through this pretty quickly, but just stop and ask any questions along the way. Mathematically, this is just algebra or even pre-algebra stuff, or sort of linear algebra, but many of you would have taken an actual proper linear algebra class. So You should be okay with this. The first operation is translation. That's just moving objects from one place to another. And the forward transform for it is just adding t sub x and t sub y. It's what we're doing with our shapeshifter operation. In vector form, we just define a single t. If we're adding t to get the forward transform, the inverse transform is just then subtracting t. You can kind of see how this is a linear operation in that sense, right? If we have these three vertices that compose a triangle, we apply some translation vector to it of +4 in the x and +3 in the y. What do we wind up with when we apply it? We wind up having a triangle that's shifted over to the right 4 and up 3. If we want to move it back, we would then just subtract 4 and subtract 3 from every point that is going through. I don't know how much I have to belabor the point. Here's our translation example. We just add stuff. We can handle that. Changing an object size, that's otherwise known as scaling, that is a multiplication. So again, our shapeshifter is doing that as well. We're taking every value of x and y and we're multiplying it by some scale value. Generally for this, we think of the scale value as being a positive value. You can think of negative scaling and it has some meaning, but it also winds up implementing a reflection as well over an axis. But still, you can think of just for positive numbers, we have s sub x and s sub y. If s sub x is greater than 1, every value of x is going to be moved to some larger value of x. If it is less than 1, it's going to squish, right? It's going to take every value of x and make it some value that is less than x. So it's just multiplying by those scalars, but in our matrix formulation, it winds up being the diagonal that we're multiplying it by, right? You don't have to take my word for it, right? Where's the full vector formulation here? If we have a value here and a value here and zeros for b sub x and a sub y, when we do our dot product here, right, we get a sub x plus p times p sub x plus 0, and then we get 0 times p sub x plus b sub y times p sub y. That gives the values scaled by both that x and that y parameter that we have here. So that winds up being kind of that diagonal matrix multiplied by our input value here. For the same triangle at the same locations, if we set our scaling matrix S as just 2 and 2 on the diagonal, we wind up with an equivalent perspective proportional scaling here by a factor of 2. This vertex, which is at 1, 1, goes to 2, 2. This one that is at 3, 1 goes to 6, 2, etc. The end result is a triangle that is larger. The end result is also a translation, or at least in effect a translation, because that scaling is relative to the origin, relative to 0, 0 here. So it is both getting larger and it is moving away from where it was relative to the origin beforehand. It's just a function of the multiplication of our x and y values. If we want to scale around a point, we would have to compose those transformations. We would have to scale and then transform or translate back to where it was originally, with the inverse just being the multiplicative inverse for that scaling matrix. Okay. There's scaling that preserves angles but not lengths. We can have certainly non-uniform scales where s sub x and s sub y are not the same value. They certainly don't have to be. That was in our shapeshifter example as well. That preserves our lines, but neither angles nor original lengths. We can have reflection about the x-axis without any other scaling by just setting s sub y to -1. I think intuitively that might make sense, right? If our point was 1, 1, if we now make it 1, -1, that rotates it around the x-axis. We can also rotate it around the y-axis using a similar concept. And then if we set both s sub x and s sub y to -1, we wind up rotating around that line y equals negative x. We're reflecting it about the entire origin here. We can also transpose our x and y values, which gives us effectively a reflection about the line y equals x. If we want to just swap the values, what was x is now y, what was y is now x. We think of that as a swap operation, but our matrix allows us to do that as well, right? if we set the output matrix such that we want x prime to be equal to y, we want y prime to be equal to x, well, our matrix vector formulation allows us to do that as well, right? We would take 0 times x plus 1 times y and have that be our new x value. We then take 1 times x plus 0 times y, have that be our new y value. That gives us our transpose of y and x, and in effect that allows us to reflect around the line y equals x, with the inverse transformation being that same exact matrix. If we want to reverse the transposing, we just transpose again one more time. Does anyone know how to do rotation? Think back to high school, middle school, whatever you would learn this. How do you rotate a value? Okay, good. It's new. There we go. Shouldn't be too new. I mean, you should learn it in a lot of different contexts, but this is just in the 2D computer graphics world. One way we can do so is by converting to polar coordinates. This is now starting to sound a little bit familiar here. I mean, what does it really mean to rotate, right? An individual point doesn't have any meaning when we think about rotating, unless we're talking about rotating around a point. So we can think about taking that vertex and rotating it around the origin. So one way we could do so is by first converting that to polar coordinates. And in converting to polar coordinates, it's no longer x, y, it's a theta, an angle off the x-axis, as well as then some radius, right? Some length information associated with it. So we would first do that conversion to polar coordinates. Got the distance, can calculate the angle based on our arctan function. We can then recognize that doing our actual rotation is going to correspond to just changing that value of phi in this case, where we have a current value, we then may want to rotate it by either increasing or decreasing that, and then using one of our laws of sines and cosines, we can then add the values here. Okay, that's our conversion to polar coordinate. When we rotate around the origin, we have a new angle that we're calculating here. So we add that angle to our original angle here, use the sum of angles formula, which looks really complicated in terms of, but that's something that you may have learned in a trigonometry class, where if we have r cosine phi plus theta, it's equal to r cosine phi cosine theta minus r sine phi sine theta. That doesn't look like it fits into our matrix formulation, but again, recognizing that our original value of x and y can be interpreted as r cosine angle and r sine angle, we then have those terms represented here via our sum of angles formula, substituting x and y back in, x and y, we wind up with a pretty well-known rotation matrix that given a value we want to rotate our vertex around the origin by, we do cosine, negative sine, sine, cosine. I think memorizing that is probably sufficient. You know, I don't overthink it too much, but it is a direct application of converting to polar coordinates, adding an angle to our original angle, and then applying the sum of the angles formula, substituting back in our values of x and y. So it looks non-linear to us, right? Because it looks like it's taking a value and it's multiplying these trigonometric functions to it, but those would then just be constants, right? So this matrix, well, it looks like it has a non-linear term here. This is constant for the angle that we want to rotate by. So we are just taking our x and y and doing our matrix vector multiplication of it to get a rotation by that amount of theta around the origin. The inverse rotation would be that same matrix, just plugging in negative theta for theta, and then you get a very similar looking matrix here where just the negative sign for the sine term is the case. And the end result is an object that is rotated around the axis. Right-hand rule about what is positive or negative. There's all sorts of right-hand rules for doing rotations and looking at 3D geometry. Personally, I don't overthink it too much. I try positive theta, and if it's wrong, I try negative theta, and I'm happy with the result. It is always one or the other, so you really can't mess it up, more than once. You can't get it wrong twice, and I think that's not a terrible way to think about, all the various positive, negative axes in doing your OpenGL. I wanted us to do an exercise where we by hand do this rotation, but I don't want to, make sort of a silly exercise. I guess we could show that it's still a linear transformation Any of our primitives here is just a collection of our vertices. We can think of this as a quad. We could have just done a triangle as well. Given a value theta, 30 degrees here, pi over 6, there isn't any actual work to be done, right? You have to then calculate cosine and sine of that 30 degrees, and then just do the matrix vector multiplication. As I had this exercise where we were going to do this by hand, I thought, well, you know, what year is it? Let's just do it via MATLAB. So here's our MATLAB code for the same. Given our square with just x parameters and y parameters, can you guys see that? Okay, here it is awfully tiny. Again, correspond to those points. The x values are 6, 7, 8, 7. The y values are 2, 1, 3, 2. And then if I want to draw them all connected, I add a fifth point to kind of go back to the beginning here. That's just a MATLAB thing. There's our value of theta. We then plot that initial square, set the axes accordingly, and keep the axes squares so squares look kind of square. We then just define in MATLAB our actual rotation matrix there. So there's our 2 by 2 rotation matrix of our cosine, negative sine, sine, cosine matrix here. We are then, and of course MATLAB makes what otherwise is a lot of code in other frameworks and languages, makes it very easy. We just do r times the square to get our rotated values for all of those points, and we plot that value as well. So this was meant to be a paper and pencil exercise, but we're engineers. we don't need to do that. We can just write the code itself, and there's our rotated, reasonably square looking square. I asked for the axes to be, maybe that's an optical illusion, I asked for the axes to be kind of square, but they don't look that square. That looks a little bit better to me. But what this was then was for those same points as we had on the slide here, which as the first graph, it draws it as blue. Just those points, I just asked MATLAB to connect the dots and make it a line here. Kind of like a primitive assembly. We can't do the rasterization easily in MATLAB, but we could probably have filled it in some way. And then as we apply that matrix to all 4 of those points, kind of independently from each other, or you can think of it as being done all in parallel to each other. As we perform that matrix vector multiplication, each of those points are individually moving, but in this case, the rotation preserves our lines and our lines of parallelism. It is that kind of nice property that what was a triangle beforehand is still a triangle after we've done that rotation.
What point is it rotating around?
Around the origin. Yeah. So that's another question. So as we talk about composing these transformations, maybe I'll try to bring the MATLAB back, although doing live MATLAB in class is always a recipe for fun. We don't always want to do that, right? Just like we don't always want to scale relative to the origin. Maybe I want the square right there, and I want it to just grow around its own origin, right, or its own center point. We may also want to just rotate something in place. But maybe you can kind of think your way through it a little bit before we get to it. Eventually, the actual matrix itself, like the values, is no longer intuitive once we start to combine these transformations. But it's all kind of logical. So we're always rotating around the origin when we apply this cosine, sine, negative sine, cosine matrix. If I wanted to rotate that shape around an arbitrary point, or around its center point, what would its center point be? 7, 2. Okay, yeah, right? 7, 2 would be its center point here. How could we go about doing that? If you looked ahead, that's cheating, but that's fine. How could we go about doing it?
If you move the shape to the origin, like the center point to the origin, and then rotate it and move it back.
Move everything to the origin first, and then when you rotate around the origin, it is rotating around its center, and then just move it back. We can do that via a series of steps. Let's try it. Oh, what could go wrong? What would be the right? Well, there's 5 points there, so we'll just call center equals. We said 7, 3. Does that sound right?
Yeah, sure.
Okay. 7, 2, yes. You're going to let me go wrong here. So we could first just move it. So, okay, we plot it, we do that. That's our rotation matrix. That's square, we could still do square 2. Square 3 equals square 2. What should we do with it? Square 1, excuse me. Square 3 is the original square with what? We want to move it to the center. Move to the center, to the origin. We're going to learn a different way to do it, but let's do it this way first. Move it to the center. Move it to the origin by subtracting the center from all those points. If we want to test that, we can still do that too. Just to confirm that we actually did move it to the center. Well, our axes are no longer the right axes, so now we have to go a little bit negative here. So we want to see something at the origin. Looks good at the origin. But now we're not going to need that, so I'll move it back to where it was. Okay. We want to move it to the origin. Now we want to rotate it, right? And that's, we can keep it the same. Use the same value. Move back to original location. And there's our nice rotated square around its own origin. That is still, and there'll be a point to this in a minute here, that, and we better get to it, that is still a little cumbersome in some sense, right? I mean, rotating around the origin was a nice single matrix vector multiplication. Rotating around its own center was a translation, a rotation, followed by a translation. I mentioned that like on slide 3, but the point may not have been that clear, but we can kind of see it now, that we want to get rid of those extra steps. We want, in our formulation, to set up our translations such that we don't have to do multiple things. We can just set up a single matrix. And I'll show you mathematically what that winds up looking like in practice. We'll go back to our matrix there. Shearing is something we may also then want to do. That is translating x in proportion to y. And for the x-dimensional shear, we can also translate y in proportion to x. That requires then taking our value of x and including the value of y as part of its own. You can think of it as a scaling in that direction as well. So this is an example shear in the x dimension where we take our value of x, and we're adding some constant times y to our new value of x. That takes our square, and it still preserves our lines, but no longer our lines of parallelism originally. Doesn't preserve our angles, excuse me. And so our values of y don't actually change at all, but our values of x are changing in proportion to the amount of y values that we have there. We can also do the same exact thing in the x dimension. Another way to think about shears as being rotating one axis but leaving the other axis unchanged. Ultimately, it's good to have an intuitive understanding of what is happening mathematically here. One important takeaway, and if you want to just kind of leave it as one takeaway for this whole series of translations, rotations, and shearing topics, is for all of those so far, we can represent it with 4 values in our matrix. And that's probably a sufficient level of understanding for us. And we oftentimes do not have to manually derive those values ourselves, but we do have to think in terms of, okay, what is my object? Where did I specify my geometry? What does it now mean to apply these transformations to my geometry as they come in? So this is the example of what we just did. How do we at least start to do more complex transformations? How do we rotate an object around a particular point other than the origin? So for this example, can we scale by 1/2 and then have it be rotated at a 30-degree angle? We can, right? We can take those matrices and we can combine their operations before doing the matrix vector multiplication for our incoming vertices. So for this composition, it actually works out even simpler for us. Scale by 1/2 at a 30-degree angle. That's kind of an ambiguously termed thing. The idea is we're doing rotation and then scaling and then rotating back. So you would just do those steps. You would determine for our rotation of our value what that matrix for our theta value would correspond to. We then would have our scaling matrix S for scaling by a factor of 1/2. Then we'd rotate our matrix back using effectively the inverse of that matrix operation for the rotation. And the final result of our rotated, scaled, rotated back vertices would be those input points which is the output of the second stage, which is an output of the first stage, and you can think of those matrices as all being kind of combined into just one operation here. And this is the case for any sort of composition of at least our matrix operations that we have here. You can take the matrix that would correspond to a rotation, multiply it by a matrix that corresponds to a scale, and you get the end result of having done both operations for effectively as many of those operations as you want to kind of chain together. All of those matrices being multiplied together for a given frame, for a given view of our scene, all that matrix multiplication only has to get done once, right? Per set of operations we're interested in. And then the resulting matrix, the final kind of transformation matrix, is that's really all that the device needs to know about. You would send just that final matrix in, then every point would then get transformed by that matrix. Same exact example here. Scaling object in an arbitrary angle theta. We used the example for 30 degrees there. The end result matrix, when we do those multiple transformations, winds up looking like something that we kind of lose an intuitive understanding for why the values are what they are. For a 2x2 matrix, there's just, of course, infinite number of combinations of what our values for those 4 entries in those matrices are going to be. We could still do multiple matrix multiplication before doing our matrix vector computation. That is valid code. There sometimes is a reason to occasionally split up our multiple transformations into separate matrices and do one of the matrix multiplications on the device versus doing them all in advance before sending that final matrix to the device. But it is inefficient from a performance perspective. There may still be many, I think, more vertices than there are matrix values we have to worry about. But still, if we're having to do that every single point along the way here, it's kind of inefficient, right? We're doing all this matrix math when the end result from the vertex shader's perspective is kind of a constant operation that we could just do once and kind of just store the result here. Our matrix multiplication is associative. You can multiply all those matrices together to get a final matrix M here, and that's, for most use cases, going to be much more efficient, where our job from the software application perspective, when we understand what kind of transformations, what kind of translations and scalings and rotations we want to do here, our job is to calculate this final kind of viewing matrix M here. We send that final value, and then that value is what gets multiplied by all of our vertices as they come in. The quote-unquote downside of this approach is that when looking at the individual transformation matrices in isolation, we can reason about the values pretty well. If I see cosine and sine terms, and we see the kind of the sine and negative sign, we know it's a rotation. If I see values on the diagonal, we know it's a scaling operation. Once we start to multiply these matrices together, the resulting matrix is correct in terms of applying all those transformations. It just, we lose kind of the intuition for why the values inside that matrix are what they are, because they look kind of like arbitrary values at that point. Matrix multiplication is associative, but the order of those matrices absolutely matters. So we do have to be careful when we're doing these composition of transformations that we're thinking about which things we want to do first, followed by which other things, and we're setting our matrices accordingly. If we were to do rotation followed by scale, we will get a different result than doing scaling followed by rotation. One result's not necessarily better than the other, we'll just get different results. It'll be a different transformation being applied here. This is the example we just did with MATLAB, right, which is a rotation around an arbitrary point. We did it around the center of that cube. This is the point that's kind of the center of that triangle, rotating around the point 2, 2 for our triangle here. We first apply that translation to the origin. We then do our rotation around the origin. Then we do our translation back. This composition is different than this composition, right? Where if we were just doing rotation and scaling and shearing, is a single matrix vector multiplication. That is efficient. That is the way to do things. Whereas I'm showing you here, if our composition involves a translation as part of the operation we're interested in, it's many more steps. So there's a little bit of, at least conceptually as these concepts were originally explored, a little bit of an extra hurdle there or an inefficiency there if our composition of transformations involves a translation along the way here. That's our example here. This is exactly the example that we just did in MATLAB. So this, except for 2 being the point we're rotating around, is doing exactly that. A translation vector, a rotation matrix, inverse translation vector gets us that object rotated around that particular point. This is a nice visualization, but what's the nicer visualization is doing it in MATLAB. And again, this is a nice way to show that we're translating the individual vertices. The end result is the original primitive itself via that translated and rotated around that particular point. MATLAB probably was better for visualizing it than the PowerPoint for this. The solution to this so-called problem, and here's the problem statement here, is that we have rotation, scaling, and shearing as a matrix operation. And composing them is involving doing matrix multiplication to determine a final transformation matrix and then doing matrix vector multiplication here. That is for those classes of transformations. Whereas for this other class of equally important transformation of doing translation, that involves a vector addition here. The idea and the main innovation is that there is a method by which we can treat all the transformations as the same and treat all of them as just being a composition of a singular matrix that we're multiplying by. The solution is referred to as homogeneous, however you want to pronounce it, coordinates, homogeneous coordinate systems in which we're treating everything of a similar type or everything is the same or similar in nature. Conceptually what we're doing, and I think from a mathematical perspective, it's easier to reason about than as we start to try to visualize what's happening in that additional coordinate system for homogeneous coordinates here, is we're going to increase the vertices, the points dimensionality. Here, although that looks like it's 3D, we're really still thinking of 2D representation of objects, but we're adding a third coordinate, which is not Z. We're adding a third, the homogeneous coordinate W here. If this was a 3D example, we'd be adding a fourth coordinate called W. So instead of X, Y, Z, it would become X, Y, Z, W here. We then can define in our Cartesian points that we have 2 different points are homogeneous if they represent the same value X and Y for some scaled value of C here. Let me try to visualize what's happening on the next slide, but then I think what you'll see is, well, it works, so it's probably good enough for our purposes, but visually what's happening here is that our XY plane that we think of is actually just one of an infinite number of 2-dimensional subplanes in a 3D viewing of our space. So our homogeneous points have 3 coordinates. They're still representing and correlate to positions on the 2D plane here. So a value of X and Y, 1, is going to be an equivalent point that it correlates to 2x, 2y, 2, and 3x, 3y, 3, where that third dimension in W here can be thought of as one of an infinitely many number of 2-dimensional Cartesian planes for which you could think of it as a translation factor in that third dimension here. Any value of W is valid except for W is 0 for this reason, as we will see here. So xy1 is equivalent to 2xy2 is equivalent to wx, wy, w in general. For simplicity, we almost always choose w equals 1, and we'll see why that's the case in just a moment. So this doesn't solve the problem as of yet, but this is just another way to represent our xy data here. It seems like we're doing more work, and for a brief minute here we are. It's to solve this problem, as I stated, of can we treat our translations as just yet another variant of our matrix vector multiplication? We can do the translations without it, right? That's what this MATLAB code did for us. Via just adding translation vectors, we are done. If we now think of what is these 2-dimensional points as being one of infinitely many versions that correlate to other things in infinitely many 3-dimensional planes here, we can add that third dimension W here. That is going to allow us then to do translations via the use of that third dimension. So for 2D points, 2D transformations, the points are now 3 vectors, and our transformations are now 3 by 3 vectors. So what does the translation matrix look like? We can just kind of derive it, I think. We want to translate a point P to P prime. And I'm telling you, I guess this is a little backwards, but I'm telling you there is a matrix that allows you to do it now. So we know what the end result should be. right? We're doing a translation of x to x prime and y to y prime, where x has some value added to it and y has some value added to it. And I'm telling you, there's now, given our input, there's a matrix that can give us that translation. And to be honest, you can just kind of solve it, right? I mean, I don't think it's anything more than that we have these two unknowns. We effectively are going to have three equations for those two unknowns. There's going to be multiple solutions that will work for our purposes here. So we want to get a value of x plus d. That has to be equal to t11 times x plus t12 times y plus t13 times, in this case, w, or just we set 1 for convenience. Same for that next matrix vector multiplication to calculate a value of y plus d. And then the end result of t31, 32, and 33 should be our value of w here, which we're setting for convenience sake to be equal to 1. So another way to look at this, we want to get, and there's two unknowns and three equations, so there are infinitely many solutions to this. But for example, we want to get a value of x plus d sub x. So what should be the values we set for this first three values in the matrix, the first row of that matrix? There's infinitely many solutions, but give me the obvious one, I guess. What should t11 be? Just 1, right? We want to get the value of x back. What should t12 be? For just the translation, it should be 0, right? We are just not taking y into account at all as we're moving our x dimension. And then t13 would be then the value we're translating, right? That would be our d sub x. Same for the next row as well, right? This should be 0, this should be 1, this should be d sub y. And then finally, this should be 0, this should be 0, and this value should be 1. You can think of it as a mathematical trick. There may be some very deep theory that I personally haven't fully comprehended behind it. I think the long and short of it is it kind of works, right? This is now a translation matrix that does effectively what our vector addition was doing for us previously. And they're all going to kind of look like that. Yeah, we can also kind of intuitively look at it and see, yeah, that does actually move our points by a value of 4 and 3 in the x and y dimension here. But if you need to convince yourself, you can see it, right? 4 and 3 is our basically values. The rest is just an identity matrix, so it doesn't change things at all. We take 1 times x plus 0 times y plus 4 is our new value. That moves it 4 in the x dimension. Take 0 times x plus 1 times y plus 3. That moves our value 3 in the y dimension. And the math works. Right? That's one way. That's one conclusion you can make here. We've added this additional coordinate. So even when doing 2D geometry, we have a third dimension. When we do 3D geometry, we are adding a fourth dimension. It's just easier to draw the two-dimensional cases here. And so there's that overhead in some sense, but the benefits are definitely worth that additional overhead that we would have here. Yeah, sure.
I just want to make sure I have this right in my head.
Sure.
We add the third dimension W, so we can do multiple translations and things in one step.
In one step, yeah.
Okay, instead of doing everything separate.
Yep. What we saw is that for scaling, for example, I can scale as many times as I want and just generate a single matrix that gives me all those scalings. Same for rotations and shears. For translations, it required that additional step of moving back to the origin, moving back, to the center point we're interested in. We can now do those same translations just by also generating a matrix. So the benefit is it's all just a matrix at the end of the day.
Yeah, it kind of seems like you'd always just have W as 1. Is it
For these type of transformations, it's always going to be 1. We'll get to it next week. It's not going to always be ultimately 1. Oftentimes, this value is very often going to be 1, but the end result may not be 1. And we wind up shifting up a coordinate plane from where we originally wanted to be. Once we have done that, and we have a value that's not 1, we actually, for correctness, we need to get back to a value of W equals 1. So right how we saw that 7, 7, 1 is equivalent to 14, 14, 2. Just another point in that third dimension that we have here. What we have to do after our vertex transformations, if we wind up with a value for which W is no longer equal to 1, we then have to divide everything by W. And we don't do that in our hardware, and that's why our cube, if we have perspective transformations, doesn't look quite right. But for the kind of stuff we're talking about today, W is always 1 as an input. That's kind of the default assumption otherwise. And our end results for anything other than an arbitrary matrix we come up with would also be W equal to 1 for that. I think a couple of you got it. Let's take a couple of minutes and discuss with someone next to you, what would the 3x3 matrix look like for scaling and for rotation? And take just a few minutes. There's a couple helpful math hints along the way.
I don't know, man, matrices are hard. I never took linear algebra. I'm guessing to scale, since it's SY, we just add SW, or SY at XW, and that same identity diagonal.
I think you just have like, basically the 2D part of the matrix, like the 4 coordinates, would be like the rotation matrix, and then on the diagonal you have the S scalars, and then you just have like the 1
Add an extra
W, and you add like the translation stuff, the regular column. Right?
Yeah.
And you have like,
So is the idea that when you're like moving up in 3-dimensional space, it's just inherently shifting you, and so you're using that to then collapse back down to where you want?
Well, that can be the case. I think another way to think about it is that for a given 2D plane, it can be thought of as one of many possible infinite number of 2D planes here. And for now, I think it's reasonable to say that's kind of a mathematical trick that allows us to do these operations via just representing a matrix. So I think you had it, though, for what the scaling matrix would be. It's exactly the same as what it was before. It's 2x2 matrix for the x and y stuff. We don't change the w at all. So that would all just be, that'd be 1. That'd be an identity value. And it's maybe a little harder to see for rotation, but it's actually the same thing. It'd be the same rotation matrix for the x values and the y values. So the upper 2x2 of that 3x3 matrix would be the same, and then just identity for the w as well, with everything else being zeros. So really the matrices are still effectively the same once we go from 2 to 3 dimensions here, or 3 to 4 dimensions. We can try composition now and see what that would look like in practice, because that was the whole point. That was the whole reason we're doing this homogeneous coordinates. But I don't trust myself to not do it without a new file. Because now there is a third dimension here. So we would be specifying our geometry with that dimension. So it's only 5 points listed because we're kind of just repeating the original point to get it to finish up the square. Okay, that's our new square. It's a 3-dimensional square, but we should be able to plot it exactly the same way. We have our same center. We have our rotation matrix. Cosine of theta, negative sine theta, 0. Sine theta, cosine theta, 0. And for the final value, 0, 0, 1. We're keeping the original value of w there. So now we have our rotation matrix. We then, instead of this center stuff that we're doing here, we can then define our translation matrix as being what we showed here with regards to what translation would now look like, which is basically an identity matrix with the values we want to translate by. We need to kind of do this twice though, right? Because we first, like we did previously, we need to translate to the origin first. 1, 0, we'll just manually do it, that's fine. 0, 1, negative 2, 0, 0, 1, 1. That is, we want to translate first, then we want to rotate. So we have now those two matrices, and we would just be multiplying them together, in which the order does matter.
why is the third row 0, 1, 1?
I gotta close out this figure. Why is the third row 0? Did I have it wrong? It should be 0, 0, 1. Seems like it still kind of worked though, but I had all the other stuff on it. And, the axes are still wrong. That does look like it is working. I mean, it's kind of hard to tell because the axes are wrong. But then we have to kind of get the inverse of that translation matrix.
Can you print out the original original square too?
Like print out the value of square?
Like just on the
I think that
shape.
blue one was.
Oh, that was.
Yeah, that was the original square. We then want to have the translation back matrix, which is basically the same thing, but the only difference is now we're translating back, so we're going up 7 and back over 2.
Oh, we didn't move it back yet.
We haven't moved it back yet. So we did it here in 3 steps. I even added some nice comments. We moved to the origin via vector subtraction. We rotated via that matrix vector multiplication. Then we moved back to the original location. And here now we're doing all 3 of those via matrix operations. And the order does matter. So it is kind of right to left in the sense of translate to the center, rotate by 30 degrees, translate back to where it was. If I did those in the wrong order, it would be wrong, right? It would move it further off in that direction, then rotate it, move it back. So it would be not what we would want here. And there's our nice rotated around the origin. Still not very square looking, but that's just some MATLAB thing. There you go. Now it looks more square. MATLAB issue there. And that's all via single matrix. I think it's, kind of belaboring the point that if we wanted this, we know we're going to be doing this over and over again, our equivalent code somewhere in the system would be closer to this, right? Where we would do all that matrix multiplication once or first. Because we really care about the final resulting matrix that we have here. And now what would actually run in our vertex shaders would just be a single matrix vector multiplication. Again, the matrix at that point, we lose a little bit of intuition for in terms of what these look like, right? Our rotation matrix, they're all going to kind of look like that, where there's a cosine, negative sign, sine, cosine kind of terms here, right? So it'll have that kind of pattern to it. Similarly, the translation matrices will look very similar. When we see our kind of combined matrix at the end of the day, and that's M that we have here, maybe you can still look at that and kind of see what it's doing, but it's not, to me, it's not as obvious anymore, because that combination of translation, rotation, and translation back leads to a final translation that is kind of hard to visualize, what it's actually doing there. The end result, of course, as we would expect, is still the same here. And I had to think of some more interesting examples beyond just translation and rotation, but it's as many of these as we want to do at this point now. It's kind of infinitely composable in some sense. I think in practice there's just a limit of how many translations and rotations you want to do at any given time, but anything we can fit into a 3x3 matrix as an individual transformation, we can then multiply by the current transformation matrix to get our final transformation matrix. Sure.
I'm trying to see how this translates into application versus the shader. And so would you do all the calculation and find the matrix in the application and then just send that one matrix to the shader?
Yeah, and in part it depends. And we haven't talked about proper classical viewing yet, but just to show, here's our favorite happy baby seal, flex seal application, and that is basically what it is doing. And of course, I have to find the actual code where this is happening. Initial values for viewing and lighting. This is some stuff we haven't covered yet, so I'm getting a little ahead of myself. But it's just matrices being used to view objects, so it is still the same math that is happening here. And there are functions in the GLM library that basically every single one of these functions is calculating a new matrix for you. And the names of them are kind of okay. In this case, we're saying, I would start with this one. Again, it's C++. We haven't talked about it very much at all. But GLM translate is kind of what it sounds like. Translate by a certain amount, by a vector amount. In this case, it's 3-dimensional. Translate 10 in the negative z direction. Move my object 10 units in z away from where I currently am. Start with an identity matrix, which is don't change the geometry. Now I have a new matrix, which I just happen to call view translate. Move it 10 spots away. Move it away from the camera is what effectively that's going to be doing here. That result is also matrix. I then want to now rotate it. I have a happy seal. I wanted to kind of rotate. We saw that right here. Given a value of rotation we want to do, take as input the prior matrix, and this function now calculates a new matrix, rotate around an axis by a certain amount to give us a new matrix. We also have rotation in the x dimension. I did it separately. And then finally, I want to scale by a certain factor at the end of the day. Here, I did it separately, and the end result is via that matrix metric multiplication. It is doing classical viewing where this is just arbitrary transformations, but it is effectively exactly that. Each of those steps, whether explicitly as the programmer or via this third-party library that's doing it underneath the hood, is doing multiple matrix compositions and multiple matrix multiplications to get a final matrix that we are interested in here. That final question of who's responsible for that is only slightly cloudy by the fact that sometimes, depending on what we're doing with our application, there's more than one matrix we want to have. A final matrix for where our triangles move, and another matrix for calculating like lighting parameters and things like that. So oftentimes for the shader, see if I can find, it would be in source, where do we put these things? Common, shaders, and it was just our flat shader. Oftentimes then, there is in fact more than one matrix that is provided as input. But if we were just doing viewing, it would just be a single final matrix we are providing as input. And the end result inside of here, and I guess, for that one, maybe the MVP transform is a more fair example. The end result of what our vertex shader is doing is just matrix vector multiplication. So the user application is generally responsible for all this stuff. Where is the seal? How much is it rotated? Someone has to determine that's the user application. I press a key, it moves the object. Then the end result is we do a little bit of this matrix math on the CPU side, because the thought is you do it now and you do it just once, and then when it comes time in to translate and rotate millions of vertices, there's a lot less work that has to be done on the GPU side. That kind of answers your question. Okay. But then I think we then covered that. So composition is now we can do those steps because we have a matrix for translation versus just a vector operation for translation. We can compose as many of these matrices as we want to get our final transformation here. This is not exactly what we did with our squares in MATLAB, but it's kind of similar. The end result is, though, a matrix that I think it's harder to reason about in terms of just a set of arbitrary values that do something. So the reasoning has to happen as we're composing the matrix step by step, and then we kind of have to sort of trust that the order of our matrix multiplication matters, and it gets us the end result of the composition of all of those operations. And we don't have to trust. We can confirm the math is correct, but again, the result when we look at the matrix is a lot harder to reason about. Well, this matrix is very easy to reason about. This matrix isn't necessarily easy, but get out your calculator and you can kind of figure out it's a rotation matrix. Once we combine all those things together, it's not that obvious what the matrix is and why it should be that anymore. So I was going to show a demo of these running, and there's different ways to set that matrix. So I say hard way and easy way to set the matrix. They're complementary ways. It's not really hard nor easy. At the end of the day, we have a matrix in our code, and let me see if I have that window open here. We have a matrix in our code, and it's going to correspond to what transformation we want to apply to our geometry. So this example, I'll show here in a second, is just a teapot example. This is using more classical OpenGL, but it's doing something very similar, just using different API calls. It's doing something extremely similar. It's all about state machine. I want to set the modeling and viewing matrix. For us right now, set the matrix, I'm going to multiply all my vertices by. And then there are a series of functions that allow us to effectively change what that matrix is here. It's not, you have to look at the documentation to confirm that that's the case, because these are just API calls, and they're all changing state, on the device at the end of the day. But it is basically that concept. I want to translate it by the amount you specified. I want to move it by the amount that the user specified. And then I want to rotate it in X, rotate it in Y, rotate it in Z across those 3 axes based on the amount the user specifies. And then I want to scale it by the amount that the user specifies. All of these operations in this kind of old school classical OpenGL are updating a matrix. It's not that obvious it's doing it because you don't see the matrix. There's a function called to load the matrix if you want to see what the end result matrix is. Modern OpenGL, we do that via our uniforms. And this was also in our cube flyby, but we're saying GL uniform matrix for FV. There's a little bit of ambiguity in how the function is named. That's setting 16 values for our matrix to be uploaded. So it's just a single 16 value array we're sending to it. And we're basically then sending it kind of a raw pointer to, on our host side, what are the 16 values we actually want to then copy over. We always are going to call this function at the end of the day. We then have these helper functions that allow us to do that calculation in a relatively object-oriented, easier for a programmer to handle kind of, in a more MATLAB-y kind of way, right, to be able to do that kind of operations for us here. But you could always just kind of manually set that matrix via just 16 values that you specify. If you do it wrong, it's going to be very hard to debug, like why did my teapot disappear? Why did my seal disappear? But the end result is when we run our transformations, and this one I kept it as a grid so that, or excuse me, as a mesh, so you can kind of see it a little bit easier in 3D. And here I'm just using the keyboard, and that's just all that's changing as I change the code is the matrix. Every time I press that, it changes the matrix. It's still efficient to do that way, because even as I'm pressing the key a lot of times, and I can then scale, and one of the keys allows me to rotate as well. There we go, we're rotating our thing around. Now we have some real 3D going on here, right? All of those changes of a key press are just changing the matrix that we're applying. That changing of the matrix usually is going to then happen in the OpenGL application itself. OpenGL then sends that matrix, either via old school OpenGL or modern OpenGL, sends that matrix to the hardware. The hardware is doing matrix vector multiplication of every vertex as it comes in. And the same goes for Flex Seal, although the last time I tried it, it kind of hung a little bit. Where's my Flex Seal?
So how would this relate to like a video game? Because like in the video game, I guess you would think of it as like you like the viewer like the origin.
Yep.
Not like.
Not always, right? Sometimes the camera's behind you and it's kind of third-person view, but yeah, right. You're usually the origin, sure.
So like, I guess it's just kind of hard for me to like wrap my head around how like you start with the object in this 3D space and then rotate it, as opposed to like I think you would work backwards from like you want to view it in a certain way. Does that make sense?
Yes, but we have to cover that. Another hint to the answer, and we won't get to that, that's next week's topic. Another hint to the answer is we have these matrices. One of them is called a viewing matrix, one of them is called a modeling matrix. The end result is what's called a model view matrix. They are equivalent, sort of inverse operations from each other. Another way to think about that is I have a seal, and I want the seal to be closer to the user and like larger on the screen. Do I move the seal closer to me, or do I move the camera, the object, the viewer closer to the seal? The end result is the same, right? And so we think of either viewing, where we're moving our camera, or modeling, where we move our models. The end result is still just a single matrix. You can think of it either way. So that's the operation that we have to kind of set up. That's actually what's happening in this example. It's not a video game, but we have not just a single triangle, we have a whole sequence of triangles here, and we're applying all these transformations to it. And that's where this whole now composite object should be relative to where the camera is going to be. Does that kind of answer? I mean, it doesn't answer, I know, the final question, but viewing is part of why we have these transformations. We're going to have to set up our camera and how we're going to look at a scene. The end result is still just a single matrix, as we see here, and composed of rotations, translations, and scales and things like that for where we're going to put our camera and how it's going to view the scene. The final wrinkle of a camera is we also want to limit potentially what we want to see in the scene via field of view or focal angle of our camera, and we can do that via matrix compositions as well. It gets a little bit more mathy than just these basic transformations, But the end result is still just a matrix that we're applying to our scene. So let's leave, oh, your question, sure, yeah, about the seal.
I wanna make sure I understand what the CPP file is doing there
Okay.
about the seal. So in this case, the seal is not happy to see us, we're happy to see the seal, and we're bouncing.
Well, that's a semantic point that I don't know actually the answer to.
Okay, well, in the CPP file, the view is moving rather than the seal moving.
I did both, because
Okay.
certain, we haven't covered this yet. Certain things it matters to have relative to the model, and certain things have to be just relative to the camera. The end result is a final matrix that is really either or both, depending on your perspective.
Does both, okay.
It is effectively both, right? I guess translate's probably the easiest way to think about it, maybe. When I called GLM, well, in this case, it was just hard coded. You don't. Okay, there's a separate translate here. There you go. Create a matrix, create a vector called GLM translate. Who am I translating? Well, in every sense, I'm translating my vertices, right? That's the matrix that gets multiplied by my vertices. So it's my model that I'm translating. But what does it mean to be -10? That's where it's both the camera and the model itself. Who is -10? Well, it's -10 assuming a camera is located at a particular location, and we don't have, we do, but it's kind of hidden. We haven't talked about this yet. We're setting up a camera at a particular location that we're looking at for the particular scene, and so 10 is relative to that here. The order of these operations for the same reason also do matter. So are we moving the model 10 units negative away from us, or are we moving our camera 10 units away from where the model is? It's not really one or the other. It's kind of both. And I think that's why it's still, even, you take this class, you're still not going to be an expert in OpenGL and graphics programming, because that's the kind of thing that you really also just have to really experience to get a more intuitive understanding of what does it take to take a model and have it look like the way I want it to look for that particular scene. Let's leave things here with a relatively happy seal and pick up on Tuesday.